Good afternoon, everyone. I welcome you all for the final session of today's FDTP. For today's session, our resource person is Dr. PM Arun Kumar. Dr. PM Arun Kumar is currently working as Associate Professor in the Department of Computer Science and Engineering at Karpagam College of Engineering, Coimbatore. He's an accomplished professional from the teaching fraternity within 17 years of experience. He carried out his research in the area of wireless video QoE and has published more than 15 research articles in reputed international journals. His research interests include machine learning, wireless networks, medical informatics, algorithm design, and data analytics. He has received funds from various government agencies such as CSIR, DRDO, and ICMR to conduct workshops and seminars. He has acted as a reviewer for many international journals. He has a Green Belt certification and is awarded Global Career Counselor from University of California, Los Angeles. He has acted as keynote speaker at various institutions and has delivered lectures in the broad areas of engineering, cognitive psychology, and management. He has more than 50 certifications from Coursera, Allison, and NPTEL and Accenture. He is an articulate communicator with demonstrated ability to teach and motivate students at the highest level. Thank you. Over to you, sir.
Yeah, thank you. Thank you for the introduction. Hope I'm audible to you. Ashwati, can you check whether I'm audible? Yeah, very good evening. Hope I'm audible to you.
Sir, yes, sir, you are audible, sir. You can proceed.
Thank you so much. Right. So, very good evening to one and all, and definitely I'm happy to address a small lecture on topics related to graph and in particular in specific to the course data structures with respect to this 6-day faculty development training program. Definitely, I would like to thank the organizers for having given me this particular opportunity to interact with various people in teaching field. And with that, let me go into my topic. And the topic for discussion for this particular session is on graph traversals and heap implementation of both traversals of a graph as well as heap, and how far you are going to implement heap. So data structures is a very, very important course, irrespective of the universities or irrespective of the colleges, because of the nature of the course and how the relation between the course and the understanding and the linking with the need for students to get very good knowledge in data structures so as to get very good placements. It is one of the core subject where a lot of questions in competitive exams will be asked. So in any sense, data structures cannot be avoided if a student is taking a course related to computer science, whether it might be an information technology or any allied courses. This course is very, very important. And myself, Dr. Arun from the Department of CSE in Karpagam College of Engineering, we will straight away go into the topic called graph traversal. As you might be knowing, the importance of graph theory in general while we are trying to learn data structures. It is one of the very important part of data structures. Whenever we as a faculty, when we try to segregate the different portions related to data structures, maybe the initial part of say modules 1 and 2 or the units 1, 2, 3, whatever we have in our curriculum, all deals with something like a linear data structure where students will be knowing or trying to learn what is array, what is stack, queue applications. Along the way, they try to implement those concepts by using some programming languages of their interest. Then gradually, whenever when we are going into the last part of data structures, always we encounter the topic called graphs. Maybe after tree data structures. So which means both comes under nonlinear data structure. So obviously the difference between a linear and nonlinear data structure should be very well known before going into the graph and graph theories. And even when we see the applications of graph theory in general, it is phenomenal in terms of the usage of the algorithms right now, advanced algorithms, whatever we take, even which is related to artificial intelligence or even machine learning. The crux or the core thing comes from branches from graph theory in general. It's a mathematics and computer science related concept called graph theory. There emerges all those advanced algorithms. Even if you think about any field for that matter, everywhere this graph theory has been applied with aplomb. The reason for that is the application really goes to the common man very quickly and very elaborately. When you take, say, for example, networks, in general, computer networks, the relationship between different nodes, we need to study and analysis. We need graph theory. When you try to take something like Google Map, distance between two cities, the minimum distance between two cities. Maybe we might have already studied algorithms like Prim's or Kruskal algorithm. They branches from the graph theory, where we need to understand what is node, what is meant by edges, and how you connect a graph. And that whole mathematical implication can be applied to any field, even when you take very, very advanced algorithms like page ranking. Web pages, and everybody is aware of that. Ranking of web pages, we need to have some sort of algorithms running behind. And the basic thing is graph theory, where we need to assume each of the pages single node, link between one page to another page. We need to consider or assign or assume as edges, and we need to analyze that. So all advanced page ranking algorithms in web technology or in general internet technology also applies these graph applications. So it is very, very important. You tell me any area and there is an application that resides there related to graph theory. In biology, study of genes, study of protein structures, there again we need this graph theory. Anywhere, anything around the world, if you could see, even in physics or chemistry or any advancement area, this graph theory applies. So it's very, very important. It is one of the what you can call it as a bridge between the basic data structure and the advanced data structure. So that's a very important thing. Where a student, when he or she transforms from learning the basic data structure, if he or she need to go to the advanced level, I think he or she need to travel this graphs and the concepts of graphs. So that really makes this graph theory very interesting and very, very important in the context. Right now into the exact topic of interest, what you can call it as graph traversal. We need to know what exactly a graph traversal means. Traversing is moving from one node to another node, so which we call it as visiting each node and each vertex, rather we can say in that way also. So graph contains combination, or what you can call it as a collection of nodes interconnected by edges, and each node need to be visited once at least. And for that we need graph traversals. Why we need that? Because we need some automation. You just think about in a real-time scenarios where you have thousands and 10,000s and lakhs of nodes we need to achieve. And if you want to have an idea or a glimpse of the path that needs to travel or the minimum path that need to be extracted from that, we cannot go for a manual. So always an algorithm is needed. And here graph traversal algorithms plays a very, very important role. And the type of graph traversal. So when you try to see what type, the basic types are the one that need to be taken here. One is BFS and another one is DFS. Conceptually, we need to understand the difference between BFS and DFS so that the implementation process becomes very, very easy. So the type of graph traversals, as it is pointed out in the slide, we need to really dig deeper into the basic difference or the subtle difference between the BFS and DFS. That makes the discussion on the types of graph traversal. In general, you might have seen a combination of nodes connected by edges. But the thing is that directly I'm just trying to have a slide that really gives an answer for a very simple example graph of BFS and DFS. If you could see here, there is an ordering which we are trying to explore. So basically, we are trying to visit a node and explore a node. There is a difference. There is a difference between visiting a node and exploring from that node. So once you visit a node, meaning that I have reached that particular node. And from that node, how I am exploring. The exploration is nothing but trying to see the neighbors. The neighbors is a very colloquial term. Maybe you can put in as adjacent nodes. So when I am visiting a node and I want to explore more, I need to do something called exploration. So that exploration is nothing but trying to see what are all the possible neighbor nodes available and in what way you move. That defines your BFS and DFS. So that's a very, very important point here to understand. Maybe I can come back to that slide a little later. So BFS is, I start with BFS. So breadth first search is a traversing algorithm. And we need to select a particular node, obviously. From that node, maybe a starting node, trivially, you can start from any node in general. If they have been given a source node, you can start from that. And you explore. You can see here, we traverse an algorithm. Traversal algorithm starts from a particular node and actually it explores, it explores to all the neighboring nodes. At what depth and how it goes, that determines your BFS. And a very important point, anywhere we study, BFS always can be implemented by using queue data structure. It's a very, very important point. Even if we are trying to explain it to a particular student or a student batch, they need to know the difference. Really, there shouldn't be any confusion. BFS really need a queue as a data structure for implementation, and the basic queue ADT, everybody knows that it is a first in first out, where any element comes in, that is the one that gets the access immediately. So that is a BFS point. So 2 points need to be understood even before going into an example. BFS stands for breadth first search, and it is a way of graph traversal, and how it is going, it explores all the neighbor nodes at the present depth. That's a very, very important technically a definition, where it explores all the nodes. This all is very, very important. Probably we will see an example and try to justify this definition using that example. And the queue is the data structure that really needs here to implement your BFS. So I take a very simple example. This is a graph containing some nodes, say start node is S, and I do have a different node structures, and it's a typical example of a graph which I am taking, and I'm trying to apply a BFS. Before going into an algorithm, we try to see how that algorithm works. An example will give you really a good idea about the implementation process. You start with this node. Say source node is the starting node. I take this node really and try to see what are all the neighbors available. If you could see here, source node contains, there is one path here, there is another path here, and there is another path here, or I can call it as an edge. So there are 3 edges now, adjacent nodes available at the disposal for the node S, which means I need to visit all these 3 nodes first. That's the concept of your BFS. So again, the meaning here is, you just see here, you are trying to explore all the neighboring nodes at the present depth before moving to the next level. So basically you start with S. That's what the numbering here points out. Let me give another color so you get an idea. So you can see here. So this is just to try to infer what path it really travels from the source. I'm moving to this A first, one. So S and then A. Then you know that another neighbor node, I visit that also. This is the second path I explore, B, and then third one is C, S, A, B, C. After visiting these things, I'm going to the next level. So for A, once again, I do have a D as my adjacent node. I visit here, then I do move to E, and then for C it is F, and finally to G. So if you could see here, it is S, and then A, and then B, C, and then D, E, F, and G. The meaning is that we try to explore all the neighbor nodes for the current node. And we do that, and then we try to go for the next level. This is how a BFS really works. Maybe the rule here, very abstract rule point here is something like this. You visit an adjacent unvisited vertex very first time, mark it as visited, and you display it. You just take that, and then you are trying to insert while implementing. You know that we are trying to use a queue. Maybe I will give an example, very easy example in the coming slides. So we try to insert it into the queue. All right, the visited node. And what we try to do here is, if no adjacent vertex is found, then what we're supposed to do is that we do a dequeue operation in the queue, meaning that we delete the node, possible node in the queue. So always your insertion at the rear end, deletion at the front end, that concept really holds here because we are using queue data structure. And we try to repeat that in such a way that finally I'm trying to get the ordering of this, or what we call it as answer for this breadth first search. Let me go with a very simple example here. Here. So this is an example what you're trying to take here. Even before applying this queue and trying to get an answer, that's a way we are trying to see how this so-called BFS works related to queue data structure. Instead, even you can even get the answer straight away. S is the starting point, and you know there are three possible neighbors. So I need to visit all the neighbors first before exploring the next. So which means it is S, A, B, C, and then obviously this one thing left out. This S, A, B, C, and then D will be the answer. And you definitely need to know how it really works by implementing queue. So S is the first vertex which I'm choosing, and it will be coming and taken up. Once you have done that, what happens is that I have three adjacent, isn't it? So A, B, and C. So we start with an S and mark it as visited. Then what happens is that I pick up A. Again, there is nothing called an order you need to apply here. You can choose any type of a node, doesn't matter really. Any adjacent neighbor node will do. So A has been taken maybe in terms of alphabetic order for understanding. A has been chosen here, so which means I'm putting A inside the queue. Now what happens is that for the same S node, I do have another what you call it as adjacent node B. So definitely I need to insert B in the queue. So in the next subsequent step, you see here B has been inserted. And remember, maybe in this diagram, this is the rear end where I'm trying to insert the elements. And this should be the front end where we really, if we want to apply a deletion, we have to do in that way. So B is there, I insert it. Again, for the same node, what happens? From S, I have another node called C, so I am inserting that also. So basically, all three nodes gets inserted. So now we have enqueued all the three elements. Now what happens is that S doesn't have any other node. There is no neighboring node apart from A, B, and C. So what happens is that I need to do a dequeue operation or a deletion operation in the queue. So obviously, from this particular queue, A will be going out. So I'm taking A as out. So once we do that, we dequeue and find A. Once we do that, what happens from A, I do have another unvisited node, D. So I'm making that D again into the queue. So when everything has been done, because there is no other node available, I simply dequeue all these things to get the order, what we call it as BFS or breadth first search. Similarly, maybe I can go into a DFS now. Traversing strategy, just the opposite of what I am telling, opposite of your BFS. So it explores the highest depth. So this is a typical difference between a BFS and DFS. So in DFS, as you know, there you used queue. Here you are supposed to use stack as your data structure. So the property of stack, everybody knows it is a last in first out. The one that you put last becomes the very first element to access. So that's a property of stack, and DFS uses stack, an important thing. Again, a basic rule for uniformity I'm trying to show. You see here, visit the adjacent unvisited vertex as usual. Now what happens, instead of queue, I'm using stack. So I'm applying a push operation, stack push is applied and the element is done. So again, if no adjacent vertex is found, I try to pop. So here it is a stack operation for DFS, and I do the pop operation and I repeat the rule 1 and 2 once again. Maybe with respect to the same example, if you could see, I start with S. Then what happens? I have elements A, B, and C. Now the difference is that out of these three, I am choosing A. For example, A has been the first adjacent node. So I put it into the stack. Now A becomes my top element, and here comes the difference. Once you move to the new node here, I need to explore from this node. All right, so it is not exploring all the neighbors here. I start with a node, I go to the adjacent node, any adjacent node, and from that node I try to explore. That's a concept of what you call it as DFS. So here what happens is that, yeah, you have put A. Now from A, you are trying to see, is there any unvisited node? So I do have D and B. So what happens? I'm choosing D. So S from A and then to D. Now from D, I'm trying to see. So visit D and mark it as visited and put onto the stack. Here we have B and C nodes, definitely not visited. So which are adjacent to D and both are unvisited. From D, if I'm trying to see B and C, both are possible. And I choose B. Possibly I choose B. What happens is that I keep that B also. So S, A, D, B, everything done. Now you have a point. You just see here. Now I reached B. Now from B, I cannot go to S. S is already done. D is already done, which means this point, I need to call it as a dead end where there is no possibility of visiting an adjacent node as an unvisited point. So there comes a concept of what we call backtracking. Very, very important. A backtracking concept where stack really applies that. So whenever I reach a dead end, I come back to the previous node and try to see if there is any possibility. So that's why what happens for that nature, what happens when that has been reached, I'm trying to do a deletion in stack. So B has been taken away. So we pop B from the stack. We now check the stack. You can see here. So previous node, and now I'm trying to see, backtrack and see from D, is there any unvisited node? Of course, there is a node which is unvisited. So I try to visit C as my answer. Again, in terms of stack, what happens? Once I deleted that, now I have a possibility of insertion once again. What is that? I keep my C inside. Now all these things popped out and to get the final result. So this is how the traversal using depth first search has been applied. Maybe I can go with a recap so that you get a very clear idea of what is BFS and DFS really, right? The step 1 for BFS, I'm giving a little bit of an expanded algorithmic steps here. For BFS, we need Q. You define the Q, and of course, the size is equivalent to the number of vertices in the graph. In the next subsequent step, what I am trying to do is I am trying to select a particular vertex, any vertex, and that becomes the starting point. Visit that vertex, and of course I am inserting that into the queue, and I'm giving a highlighter here for you to understand what really your BFS is all about, what difference it makes. This step 3 is very important. You visit all the non-visited adjacent vertices. Remember, it is all the non-visited adjacent vertices of the vertex which is at the front of the queue, and insert them into the queue. That's why you understand possibly here, yeah. From S, I'm trying to have all the neighboring nodes A, B, C inside my queue. All right, that's the point here. So once I do that, yeah, once I do that, when there is no new vertex to be visited, if there is a condition that exists like this, maybe I need to go for the deletion. So I repeat these steps time and again. And when the queue becomes empty, we produce the final result, what you call it as BFS. Maybe with respect to an example, being a recap of what we are telling here. Yes. So consider this particular graph here, a typical graph which contains say 7 nodes and edges. And this is the graph taken. Now we are considering what you call it as breadth first search. Now you remember we need a queue data structure. Now you can easily identify how it really works. You are supposed to select a vertex and I am selecting A as my start point. So I'm visiting that, right? You visit that A has been visited. So insertion into the queue has been done. That's the color given here. It has been visited. Now the next step in BFS is visit all adjacent vertices. Remember, that's the crux of what your BFS. BFS algorithm works by this very important rule. So you visit all the adjacent vertices of what? That A vertex, what you have chosen. When I see adjacency of A is this one, and this one. There are 3 things. So supposingly what happens is that I insert the newly visited vertices into the queue. Maybe here you can see D followed by E and followed by B. I'm trying to insert after deletion of your A. So what happens is that it's a very important point how your BFS really works with respect to this queue. Now you could see here, what is the very next node for my exploration? So I need to visit all adjacent vertices of D. You know why? That is the next thing which is available for me to access in the queue. So from D, I am trying to see which are all not visited. But unfortunately, what happens? There is no vertex in that way. So I am taken up A, followed by all the neighboring nodes, say D, E, and B has been, inserted into the queue. And you remember that your insertion at the rear end here, don't get confused. This is deletion side, this is insertion at the rear end, this is your front end. So once what happens, you are having D, visit all the adjacent vertices of D which are not visited. So obviously I don't have anything because for D I have already visited all the adjacent nodes. So which means it is a case where I'm deleting that node. So I'm taking it. Deletion happens only at the front end. So I delete D. Now what happens? Only E and B are there. So now from which node we need to explore? That's very important. It is only E. So if you could see the next step, so visit all the adjacent vertices of E. That's a very important point. I'm making a point here because once A has been taken up, I have D, E, and B inserted. And remember, this is your front end and rear end. And the next possibility is trying for D. For D, there is no adjacent or neighboring nodes. That's why I'm deleting that node so that I'm taking it away. Next thing is E. When I see from E, you could see that already B has been done, but still I do have all other adjacency like C and F. So definitely I have to insert these C and F in the queue. Where it will get inserted? Definitely at the rear end. This end it will be inserted. If you could see, yeah, you can see here. Now I am trying to have visited node C and F. Yes, E has been taken up. Now C and F has been inserted because I am visited E, so that has been taken away. Now for E, there are C and F. I can place it like this. Again, the order of C and F can be anything. It can be C followed by F or F followed by C. That is up to you really. It's a choice that you can make, no problem at all. And once I do that, now we could see here, I need to check for B. There is nothing, for B, as the coloring says, the green color is all visited. Now B has been already done with, so nothing. So I delete B with no other options because there is no adjacency for B which is unvisited. So there is no vertex, I delete B from the queue. Now I do have what? C and F. Now I could really take up C and see if there is any node. Yes, of course, from the diagram itself, you could see from C there is one unvisited G. So I take off C away and of course I place in my G. Now the order in which it has been taken away, and that is the order which you can call it as an answer for what your BFS traversal. Maybe the same example would like to here. Once you empty the queue, that becomes my final answer. Similarly, I'm going for DFS, the same fashion. What is the extended steps now? Define the stack, total number of vertices equivalent to the size of the stack. Now you could see, select any vertex, the same thing. Now the thing is, I'm highlighting it. You see here, I just highlighted for your understanding. In BFS, I have highlighted something like visit all non-visited adjacent vertices of a particular vertex. Whereas here, you have a difference. Visit any one of the non-visited adjacent vertex, and you need to go in that way. At a particular point, there won't be a no new vertex, which means I am having a dead end. So I need to backtrack, come back to the previous step and try if there is any unvisited. So that is the concept. Here, there for a node, I explore all the adjacency, whereas here visit one node. If I have 3 adjacent node, I visit one, and from that node I will be exploring. There is the difference where we try to visit and explore. In depth first search, what I'm speaking here, start from a node, you go to another node, which means now you start with this particular node. Start from that node and try for exploration. So that's how your DFS really works, right? So maybe I can go with the same example, which will give you a clear thought about. Now I guess it is DFS. All right, the same graph. Now instead of Q, I have a stack. Start with A. I push A into the stack. Now you see there are 3 adjacent nodes, of which I need to pick only one. So what happens here is visit any one adjacent vertex which is not visited. So by random, I'm picking B here. So after A, B, which means this B is what? My top right now. All right. Now what happens really? From B, I'm trying to see whether there is any other adjacent node which is unvisited. Of course, yes. I have C as well as E. I go for C. So I'm moving to the next node. So I move to the next node. So obviously in stack, I'm pushing that also. So this is my top right now. Now what happens? From C, I have options of G, F, and E. I'm moving to E, for example. So I'm picking that E into the stack. From E, I would like to see any unvisited. Of course, D is there. I'm visiting that also. So I have kept here. Now you see, I started with A. I moved to B. From B, I moved to another possible unvisited. From C, I moved to E. From E, I moved to D. Now you see, I cannot move to A. I cannot do it for E because I have reached a point where there is no unvisited vertices. So that you call it as a dead-end scenario where we need that backtracking process. How would you do that using stack? Once I reach a point where I have made my D here with all the other elements inside the stack, now I need to apply my what? Pop, or what you call it as deletion in the stack. So I delete D. That's a very, very important step. You see here, there is no vertex to be visited from D. That's why I backtrack. So pop the D. So D has been taken away. All right. So once you take that away, that's what the diagram says. This is backtracking from green to red. So I'm coming back to E, the previous node, and see if there is any other possibility. Of course, the possibility is there from E. What is the possibility? F. So once I have a possibility, I push that inside the stack. So F is placed inside that particular stack. Once I place that F inside the stack, now I can make what move? From F unvisited. G is there. So I keep G. Now there is no new vertex. So you just backtrack, pop G from the stack, and then you just pop everything. F, and then E, and then C. You pop out everything, and that becomes my particular order of what we call it as depth first search. All right, so that is the difference between a BFS and DFS. While implementing, we need to know, yeah, that's the final one. So while implementing, we need to understand how it really works. As you know that the very important point here is, in general, one is visit and another one is explore. So when I try to explore in BFS, I explore all the neighbors from a particular node. Whereas in DFS, I explore to one neighboring node, and from there recursively, I try to explore other possibilities. So that's a DFS here. So when I have a diagram like this, BFS goes in this way. You start with, What happens is that from 1, you try to see what are all the things available. You see 2, 4, and 5. So after 1, I visit 2, 4, and 5. That's the way it goes. All adjacent nodes have been visited. Then, obviously, from this node, I visit 7, 6, and 3. This is my answer. Whereas DFS, I start with 1, but what happens is that I can move to any one node out of 2, 4, 5. I'm moving to 2. So now from 2, I'm exploring whether any possibility. So there I may be going here, 3. Now it's actually a dead end. So come back to the previous node. I visit maybe 6. Again a dead end. Come back to 2. Visit 7. Again a dead end. Come back to 2. Still there are some unvisited vertices, isn't it or no? You come back to 1. Now you visit 4. Dead end. Back again 5. So this is the way your actual DFS is really working. A very interesting thing. That's why we use stack for those implementations. So that's what we do. Again, a tree itself a graph. You know that a tree can also be called as a graph. So when you take a simple thing, you will understand very difference between BFS and DFS. You see, BFS is something similar to a level order traversal. You know what is meant by a level order traversal? You traverse this level and then this level and then this level. So that's what it is. 1, all neighbors say 2, 3, and then all neighbors 4, 5, 6, 7. That's what the answer for what? Your BFS. Whereas your DFS is entirely different. Maybe I can show it in this way. You see here, from 1, I started and visited 1. So 1, I move to the next adjacent. For example, 2. So 2 is my next answer. Now in DFS, what I need to do is that from 2, I need to explore if there is any unvisited. There is something. So 4. So 1, 2, 4, finished. Now it's a dead end. You see here, there is no node to visit, new node. So I backtrack to the previous node. Now you see from 2, there is always a possibility, 5. So I'm visiting that. Once I reach 5, again a dead end. So backtrack to 2. Now there is nothing. Even the node 2 doesn't have any adjacent nodes, unvisited. So backtrack to again to the parent 1. From here I have always a possibility. Move to 3, visit. Answer. From 3, move to 6, unvisited, so visited. Now 6, again a dead end. Backtrack to 3. Now you visit the last one. That's why you have got an answer 1, 2, 4, 5, 3, 6, 7 for your DFS. Very interesting and of course an important concept pertaining to BFS and DFS. When you apply, this is the same algorithm which you're supposed to do while you're applying BFS. Definitely you need a queue. You initialize the queue and try to take in the vertices, the values. Once it is not visited, you just enqueue it, mark it as visited. And while the queue is not empty, definitely you are supposed to do your DQ operations. You can write your algorithms in any way and the implementation process codes. Even for your DFS, the same thing, but the thing is that you use a stack. You need to know when to pop it out and for all the neighbors, what I'm trying to do. If it is not visited, I push it into the stack and I repeat the process. This is for your DFS. And how the recursion property applies, that can also be improvised as a programmer or as a teacher. You can give what it really makes as a recursive call in DFS for the students. So these things you can really understand. If the concept is understood, this becomes a very, very simple thing. All right. Now, as a conclusion here for DFS visits all the neighbors before visiting the children nodes. That's simple. That's what I'm trying to repeat time and again. Whereas in DFS, we visit all children nodes before visiting. I have made a mistake here. Yeah, all the children nodes. Now you need to understand the real difference here. It's like a way of telling it in a sentence or even in a descriptive way. BFS visits all the neighbors. You have a meaning before visiting the children nodes. Whereas DFS, you see here, it visits all the children nodes. That's what it means all in. So when I have a graph like this, what happens is that in depth first search, I visit here, then move to another node. From here, I try to go here. From here, I go to here. Whereas in BFS, once I am here, I will visit both this one and this one because all the neighbors need to be visited. Whereas in DFS, we just go to all the children nodes, meaning that you go to the next level, next to one node which is unvisited, next to one node which is unvisited. That's the way of exploration you do in DFS. All right. So applications here, very importantly, what are all the applications you really have for BFS in specific, shortest path, minimum spanning tree, peer-to-peer networks. There are a lot of things, crawlers in search engines, social networking website, GPS. I think all the graph traversals, even including your Facebook recommendation of friends, even then those things, the basic thing is nothing but the graph theory. Of course, all advanced artificial intelligence algorithms and machine learning are applied, but all depends on the basics of graph theory. That's a very, very important takeaway point. That really underlines the importance of learning the traversal. You just think about, there are multiple files, some thousands and lakhs of files now, and you need to access it with the best possible way. The traversal is becoming, it becomes very important here to understand and to implement in any of the real-time applications. Similarly, applications for DFS, detecting the cycle in a graph, many graph traversal algorithms applies pathfinding, topological sorting or ordering, another important thing that has been applied in many scheduling algorithms to test whether a graph is a bipartite or not. Solving puzzles, that is another important thing. All the puzzles or online or offline puzzles, whatever we create, something like maze game, where you need to apply this DFS so as to have the next possible move in that particular puzzle. So these are all some applications are definitely worth mentioning here. This is how your BFS and DFS really goes. So this becomes very important here, because all advanced data structures requires these traversals. Once students get accustomed with the implementation process, no matter what different type of question they ask, they will definitely won't make any mistake in the basic thing of understanding it, because that DFS has been applied in many applications, and they need that, as because the stack operations are very, very critical. A lot of applications requires that. So the basic difference and the implementation process are very, very important, and very much a point to ponder whenever this traversal topics have been taken. And now the very next one is heap. Heap is another important thing. Maybe there are a few topics in this FTP itself on a heap, possibly on the morning session, I guess. We definitely know to implement heap, the basic thing of the property of heap should be known very well. And a very important point, maybe in student perspective, they will be very much happier, and they will happy and easy while basic graphs or graph algorithms have been taken up. Whenever this heap concept comes in, they initially have a hesitation. General perspective, I'm putting it. Maybe people who are taken data structure course for a longer run will know that sorting. You just take an example. Whenever we take even recursive sortings like a quick or a merge, people will be interested. But once that heap sort comes in, they hesitate to learn, or rather they feel difficult even before understanding the concept. They give an aversion towards that topic, which should not be. So for that, we need to make them to learn heap with respect to applications and how and well it is important in the context. Heap is one of the important data structure, and priority queues are closely related to heap properties. So heap here is a special type of a tree that satisfies some condition, and it is a complete binary tree. Here people tend to make a mistake between what is complete binary tree, what is full binary tree, and what actually your heap really uses. And a very important point here is heap really requires a complete binary tree to process, and it contains a special property. What property? That's what mentioned here. The value of the parent node is always greater than the value of the child nodes. In that case, you call it as a max heap. In fact, the opposite of that, you can call it as min heap. Maybe I can give an example so that people can understand it very easily. All right. So what is a max heap here? It is a type of a heap where the value is, the root element is greater than the elements present in the child node. You take any sort of a tree structure, something like this. Yeah. If I'm saying this as a complete binary tree. All right, it is definitely yes. So for that, you need to see the difference between what is complete binary tree, what a sort of a graphs cannot be called as a complete binary. Complete binary tree is a binary tree, which means a maximum 2 child. And what that completeness is all about. You need to fill at both the levels. Both the levels need to be filled, and the thing exception is only at the last level. So whenever I have a tree like this, say for example, 1, 2, if I am having something like this is perfectly a complete binary tree, because for this node I have completely filled it. For this particular node I have filled it, but not this node is not filled at the next level. But not at all a problem. You can call this as a complete binary tree. Which one cannot be called as a complete binary tree? That's a very important thing. If I'm having something like this, see this one. Can this be called as a complete binary tree? No. This one, yeah, this one definitely is not a complete binary tree, because you could see here, this level is completely filled, but here it is empty. That cannot be done, because a complete binary tree is a binary tree where it is filled at all level except at the leaf level, and possibly at the last level it should come from left to right only. It's a very, very important point. That's why this one is okay as a complete binary tree, because here the leftmost last level in the leftmost it is filled, whereas here it is unfilled, no problem. This is a problem. I cannot call it as a complete binary. So difference between the complete binary and full binary should be known very well before attempting the implementation of heap. Then I give an example for max heap. As you know that for a max heap, the root value or whatever the value you take in a node will be greater than its children. I take 15, that is greater than its children. What is the children for this node, root node 15? All the nodes, every node is a children. So 15, you get everything less than 15. When I take 12, I think these things, subtree, left subtree, all less than 12. Whereas you could see here for all the values. In fact, if you could see, all the values will be less. Whatever the node you take, the children will be lesser. That's what. You don't want to confuse with the left side is small, right side is greater, as we do in binary search tree. No, that property doesn't hold here. Here, the concept here is max heap contains the maximum element at the top, or what you call it as a root. All elements children will be less. Whatever the, when I take 10, I have a, because the max heap, I have a greater value, and all its children will be less than 10. You see here, everything is less than 10. So that's a property of max heap. And what is min heap then? Just an opposite. I have the, in min heap, I have the minimum or the least value as the root value, and all the values down as the children will be greater. So when I take 6, the 6 is minimum, and all values will be definitely greater, or this root value will be lesser than all these values. You take 10, this is lesser than 11 and 14. So this is a property called min heap. And why we use this data structure, very important. There are many cases where you have multiple files where we need to find out the maximum sized file. I think heap property will go very handy there. To find the minimum element, because the reason is that once you access that element, you delete that element, or rather you access that element, what happens is that automatically the next maximum element will be at the top. Remember, that's how, and that's why your heap becomes very, very interesting. When I take this, access this element 15, what happens is that heap, due to the property, heap order property, which we are supposed to apply, what happens is that after deleting this root node, it again forms a heap where out of the other elements, the maximum element will be sitting once again at the root value. And this is where the real-time applications, where if you want to fetch the maximum element out of some lakhs and lakhs of data available, once I pick up a max element, now I again want to pick the max. You don't want to traverse everywhere. This heap property ensures that the very next maximum element will be once again at the top for the disposal. So that's why it is very much important in terms of complexity, which is another area where we need to explore the algorithms based on time and space. All right. Now let me go for application. That's what I'm saying. It is efficient for implementing priority queue. One heap sort algorithm we need to apply, and it has an n log n sort of a time complexity. It is implemented. I mean, implementation of Dijkstra algorithms all depends on. Again, you can apply heap there. So heap is an important thing. What are all the operations of heap which you need to know? Very importantly, heapify, insert, delete, and all of the things are very trivial. Extracting is empty, size, and get max. Is empty is to find an empty. Get max is finding the max element. Similarly, you can even get a get min. So get max returns a maximum value, get min returns the minimum value. But out of this, very important properties are these three. We will concentrate on these three. What is heapify property? What is insertion? How to delete it. Now let me go into an example now. So we need to understand, as because the representation is on like a complete binary tree. Say for example, how far your tree has been placed. I have been given some values 3, 9, 2, 1, 4, and 5. If these are all the numbers that has been given, and if you want to construct a heap, what I can do is that simply you assume a tree by filling all the levels. All right. So when I do that, first value 3, I create. This is an imaginary tree, assume 3. Now I need to fill both the levels because it's a complete binary tree. So I fill 9 and then 2, just in the same order what I'm having. And the next value is 1 with 4. So I fill 1 here and 4 here. And another 5 definitely to the left. So whatever the values I have, definitely I can form a complete binary tree, which is what required really. Now I have a tree like this. All right, this is an imaginary tree. Now, what I need to do is that out of this particular tree structure, I need to convert this into what? A heap. I need to convert this into a heap. That's what needed. That's what you call it as a creation of heap, or rather implementation of heap from this particular tree. In fact, the arrangement in terms of array, when I have an arrangement of a complete binary tree like this, the array will be like what? 3, 9, 2, 1, 4, 5. That's what I have given it as an array arrangement, right? Now, let me see how to implement a heap from this imaginary tree. It's as simple as that. You have to start from a particular level. Remember that we have an index position 0, 1, 2, 3, 4, and 5, isn't it or not? With respect to the array representation. Now, this heap, this particular, the so-called complete binary tree need to get converted into a heap. For that, out of my all the levels, I need to start from a level where it is an internal node, possibly one level above the leaf level. So I'm trying to see this particular level, start from the rightmost. That's how we implement really. We start with this node. What happens is that I'm going to create a max heap, meaning that max heap has a property that the root node will be greater than all its children. So when I have this particular node for consideration, say 2, I compare it with the children 5. Definitely for a max heap, I cannot have 5 as a children with respect to 2. So what I need to do is that you just swap 5 with 2. So 5 will be moving up, 2 will be coming down. This is the completion of this node. It doesn't stop there really, isn't it or not? Once I do that, next I need to come to this node. Now I compare the children 1 and 4. I think 1 and 4 both are lesser than 9, meaning that for this node, there is no problem really, no need to change anything. Once you have done that, you need to go to the next level. Now I'm trying to see this level with 3 as my node. I compare with the children 9 and 2. As because 9 is greater than 3, whereas 2 is lesser than 3, out of these, this is the only node that is greater than, which is greater than the root. So I need to swap here. So I make 9 here. I percolate down, what you call it as moving this 3 down. I need to keep it here. Again, I want to check until I reach my lowest level. So 3 will be compared with 1 and 4. What happens? Once again, 4 is greater than 3. So I keep my 4 here, 3 here. That's what the end of the whole process, where when I do that, I create a max heap. That's a very, very interesting thing. Maybe I could show you what happens really here. You see here, just the given elements have been made as an imaginary tree. Start with one level above the leaf level or your last level from the right. 2, I make 5 here, 2 here. Whereas when I compare 9 with 1 and 4, no problem, you leave it. So this becomes 5, this becomes 2. And now I compare 3 with 9, what happens? 3 will be coming here, 9 will be going up. All right. 3 will be coming here and it will be checked with 1 and 4. So 4 will be coming here and that 3 which is here will be moving to this position. Now you see what are all the values? 9, to the left 4, to the right 5, and you have 1 and then 3 here and 2 here, which is nothing but you see I have created a max heap. The largest element is moved to the topmost root position and I have the property, recursively I have the same property. Whatever the node I take, that value is greater than its children, a very important property. This is what you have to implement while you're implementing heap. So to do that, we have an algorithm, how to set my left child and right child. As because I have an array representation, isn't it or not, with 0 index, 0, 1, 2, 3, and this is what I create in terms of a tree, isn't it or not? I have something like this filled in. So this root value with index will be 0. This one will be index 1. This one will be index 2. And I do have this as index 3 and 4 and it goes on. So which means for any node, for any index I, you see, for any index I, my left child will be 2 into I plus 1 when I take this one. Say for example, this index is 3, isn't it or not? I take this one, 1, I equal to 1, which means what? 2 into 1 plus 1, 3 is my left child. Whereas 2i plus 2, which means 2 into 1 plus 2. So 4, isn't it or not? 2 plus 2, 4 is my right child. This property holds for any tree where my 0th index has the root value. That's a very important point. So you check the condition, what I have checked. Left child is greater than the largest, set that as largest. If right child is greater than the largest, you really set that right child as the largest. You just swap those elements of that index with the largest. What I have done here, compare the children and try to make the largest value at the top. This is what your heap algorithm. So to create that max heap, we need to do what we are supposed to do. Then loop from the first index of the non-leaf down to 0, and you call the same heapify operation. This is what we are supposed to do while implementation. And remember, while implementing this, certain textbooks or certain resources will have something like, this is what the thing happens. You see here, 2j plus 1 as your left child and right child. Even the standard book like Waze, when you try to see what is heap, they might have given left child is 2j and right child is 2j plus 1. The reason here is they have the manual description of starting the first index as 1. When I take first index as 1 and then continue in that way, maybe this one will hold. That's a theoretical assumption. But in general, while you are implementing, normally the index starts with 0. So when it starts with, index starts with 0 and I have multiple values represented in array, that complete binary tree represented in array, what I need to take is that it is 2 into I plus 1 for left child and 2 into I plus 2 for the right child. Whereas in certain sources, you may have 2i and 2i plus 1, meaning that I start here with 1, 2, 3. In that case, 2 into I, what happens? That is my left. 2 into 1, 2. Whereas 2 into 1 plus 1, 3, which is my right child. This holds for this property. You don't want to get confused really. Any one properly implemented will definitely do justice in understanding the concept, right? This is heap representation and implementation. So the steps is very simple. You initialize, start with the last rightmost parental interior node. That's what we did here, isn't it or not? We start with this node 2 and we really made that heap. And once I do that, I need to apply the heap order property and repeat that step until I get the final max heap. So this will give a clear idea, an example to do. So we are trying to construct a heap for the list what? 2, 9, 7, 6, 5, 8. I try to insert those elements, right? Heap construction. So whenever I have an elements like this, you understand that we create an imaginary tree like this, 2 followed by 9, 7 to the left and right, 6, 5 to this, and then 8 to this left, which means what? We are really having an imaginary complete binary tree. The thing is that this tree need to be converted into what? That's an important point here. I need to convert this so-called structure into a heap, meaning that the largest value at the top and the remaining children should be lesser. To do that, I need to start from a particular point. Remember from which point? This is the last level. You leave it, go to the very next level above, start from the rightmost. So 7 compared with 8. What happens? Definitely 8 should be greater than 7. So I have swapped here. You see here 8 has been swapped here. So I have finished this one. Now I come to this point. 9 compared with the children 6 and 5. No problem at all because already 6 and 5 both are lesser than 9. So I do nothing. So this is over and this is over. Now go to the root value. 2 compared with 9 and 8. What happens? It's very important. 2 compared with 9 and 8. When I have both the children greater, swap with the greatest children. That is the property. When I have two children which are both are greater than the root, swap with the greatest one or the largest one. So 9 and 8, I take 9, I swap with 2. So you see here, 9 goes here, 2 comes here. 2 doesn't stop there. You need to compare with the children. 2 compared with 6 and 5, what happens really? Again, 2 largest elements as child. So I have to make the 6 up and 2 percolated down. When I do that, you just see here an interesting max heap has been formed. This max heap contains the largest element at the top and the remaining elements at the bottom. This is a heap construction, what we are speaking till now. Then insertion. I think until now I'm trying to see how to create or implement a heap, formation of heap. Now the thing is that inserting a new element into the heap. Already have something as this is my already existing heap. Now a new element need to be inserted. Say for example 10. All right, 10 is the element which I like to insert as a new element. What you need to do is that try to place the 10 at the last level of the array representation. When I have an array representation 9, 6, 8, 2, 5, 7. 7 is the last element, isn't it or not? I fill it to the next level. I try to place my 10 there. So in that way, what I need to do is that starting from that level, again apply the same heap order property. What heap order property? Your maximum node, or rather the so-called root value, should be greater than the children. When I keep 10 here, now I compare 10 and 7 with 8. What happens? 10 is greater than this so-called root value. So 10 moves up, 8 comes down. You see here, still it doesn't stop there. I need to go until my top. Now you see the heapify property works from the bottom to the top. Now 10 is compared with 9. Once again, 10 should be moving there. 9 should be coming down, and again 7 and 8. So no problem, 9 settles in this position. So when I do that, the meaning, you just get the meaning here. After trying to insert a key 10, after sequence of operation, I have formed a max heap in such a way that even after inserting a new value, again I have rearranged it into a heap where out of the new values, the top value, whatever the value you have, will be at the positioning, or the maximum element will always reach us to the top. This is the insertion operation in heap, very important. So that's what I'm trying to say. There are two different ways of seeing this. When you take one index as the start index, you have 2 into I as left child, 2 into I plus 1 as right child. Whereas when you take a 0 as your index or root value, normally what we do here, something like this. When I do that, it will be 2 into I plus 1 left child, 2 into I plus 2 will be in your right child. So we just try to see different implementation process. This will be the starting point where we implement your tracking of your left and right child. And accordingly, what happens? I apply the heap order property. Right. I'm just trying to compare two different sources where your starting heap structure has been defined. All right. So this is how you are supposed to implement what you call it as heap implementation. Let me So heap, you're trying to build a heap. I think you know from the notes, your array representation, a complete binary tree need to be formed. And to build a heap, always you have a heap order property where the maximum element will be always at the top. And what happens is that whenever you try to insert an element, again you need to apply that heap property and insert that element in such a way that it again once again forms a max heap or a min heap for that matter. Similarly, while you're trying to delete, even after deletion, that heap should be rearranged in such a way that it once again stick on with the heap properties. So while you're trying to build a heap, you could see here these are all the things happening simultaneously. The tree representation and the array representation, the elements will be compared. We are trying to create a min heap out of the elements what we are doing. So this is a typical algorithm running. If you could see, all the nodes will be checked accordingly. The swapping happens in the same array. That's a very, very important point. Once the thing gets completed, if you could really see here, the elements, whatever you have taken, you see, this is a min heap which we are implementing. So the least element at the top and all the elements will be greater. Again, it recursively applies to the same concept. So whenever I have something like 13, you see all the children's will be greater. This is a min element that has been built here. Even while you're trying to insert a new element, you can really, for removing the smallest, what happens? The smallest element will be at the root. As I am telling, once that is done, you apply the same heap order property where the next smallest has been placed. So that's where this heap property you should understand very clearly. The thing is, whenever it is a max heap, the largest element will be at the top, the children will be less. Whenever I encounter a new value, I check that heap property, where if the children, both the children are greater than the root value, I swap with the largest children or the greatest children. If only one child is greater enough, you have no other choice. Take that node and swap with the root value. You repeat that for max heap. For min heap, just the reverse. So for min heap, the minimum element will be at the top and the maximum elements will be at the down. So even when you try to remove a smallest element, you see here, once it is done, it will impact and the heap order property is applied and the next smallest will be at the down. So this is how heap really works. Even if you are trying to insert a new value, what happens? You are inserting 67. 55, you can really understand how it really works. 55 cannot be here, so 55 followed by 67. Even if I'm giving another small node 3 and trying to insert, what happens? 3. Now you could see that because of the heap order property, it again realigns into what you call it as the min heap here. Maybe in this example, it's a min heap. That's why the smallest element at the top. So this arrangement really you need to understand. So as to implement this heap properties and to make the students understand. This is one thing I would like to show. And another one, maybe with respect to the topic which has been discussed today. This is for a BFS and DFS. If you could see an animation which shows parallelly how the nodes gets the access, how the nodes are visited and explored. If you could see here, very important in depth first search, you could see here it tries to go with all new nodes, because in depth first search the concept is that move to another node, explore its neighbor, one neighbor, again another neighbor. So it is going in this way. You see here. Whereas here, if you could see, when it starts, it visits all the neighbors of that node and then it moves. There is a typical difference. Maybe if you could visualize for a minute or two, you will easily understand how this animation really works with respect to your BFS and DFS. So for today's session, we have discussed two things. What is graph theory, applications of graph, and we went into what is meant by a graph traversal. BFS and DFS are very, very important. It has been used very extensively. The difference between BFS and DFS, it's very, very crucial. And BFS works with the principle of what you call it as queue data structure, where from a node, we visit all the neighbors and we explore. Whereas in DFS, from a node, we go to one of the neighboring node, and from there, I search for another neighboring node. So that is your DFS. So the difference is important, and the implementation process using respectively by queue and stack, very important process. Then we went into applications of BFS and BFS in real time, when and where it really applies, even in circuit designing, circuit boards, everywhere your BFS and DFS algorithms works. Then we gradually moved into the concept of heap. What is meant by a heap? Max heap, min heap, and to implement heap, what are all the things to be considered? And three important aspects of or process, or what you call it as operations of heap. One is your heapify, which is the heap order property, and then insertion and deletion, which actually follows that heap order property. So these are all the discussions we had in today's session. And if there is anything as a doubt or anything you want to ask me, welcome.
Thank you, sir. Thank you for the session. Professors, if you have any doubts, you can ask Arun Kumar, sir. I hope they don't have any doubts, sir. Thank you for the
ma'am.
wonderful
Thank you so
session,
much.
sir.
Yeah, thank you so much. Thanks for the opportunity.
Thank you, sir.